Hi. I want to show you guys what it looks like when in an average day in the middle of May, 2.6 million people in 232 countries around the world got hit with new malware attacks that we had never witnessed before. What's worse is that 60% of these attacks, they were over within the hour. There was no time to respond. You either got it or you didn't. We've got about 500 million customers relying on us to get this right every single day. And every day they send to us billions of questions about new URLs they're visiting and new things that they're downloading and weird behaviors that are happening on these systems. And all of this happens in an automated fashion, but if we don't get it right from the start, we failed them. So in this world where response doesn't always count because you'll miss it, many of us have turned to machine learning for the promise of prediction and hopefully the power to protect that first person that hits that new malware attack. But just like humans are susceptible to social engineering, machine learning has its flaws, and it's susceptible to tampering. I'm Holly. This is Jugal. We've got Randy here with us. He's in the audience. We are part of the Windows Defender Advanced Threat Protection team at Microsoft, and we specifically focus on using machine learning to protect that patient zero, that very first encounter. And if you just came from Rafi's talk, where he talked about you can't trust supervised learning, we actually have a very diverse team. We have data scientists, researchers, reversers, who all work together in concert to do this technology. There's no ivory tower of data scientists, right? We all work collaboratively together. We spend a lot of time thinking about how can we make our machine learning more resilient to adversarial attacks. We spend a lot of time building Monitor to see if we can detect them happening in the wild, studying the latest research papers, doing our own research. And we're really happy to be here today to share some of those learnings to you. I hope you find them helpful. Now, I know there are some experts out there. There's multiple levels of folks who know a lot about machine learning, and maybe this is sort of your first time talking about it in detail, so just bear with me for a very few short minutes while I go over a primer to get us all on the same page. There are two basic types of machine learning. There is supervised machine learning, where you take your experts and they provide labels for samples to discriminate clean from malware. You take that labeled sampled set and you train a machine learning model with it. Then the trained machine learning model hopefully can detect new malicious and clean samples out in the wild. So that's supervised machine learning. There's also unsupervised machine learning, and it's great at finding the bias that humans might have. So researchers may have specific things in mind when they write new features to detect a certain threat. But if they have blind spots like everyone else. And so unsupervised machine learning is really awesome at finding those pockets of unknown unknowns and helping surface those things so that you can provide more robust detection for the whole ecosystem. There's also anomaly detection, which isn't really machine learning, but a lot of people talk about it in the context of machine learning, where, again, there's no labeled data, but the machine looks for a baseline and then looks for anomalies outside of that baseline to try to help find things that could be anomalous and possibly bad. Today, we're going to be focusing on adversarial attacks against supervised machine learning models. There are multiple levels for client-based protection where you can apply machine learning. Very simply, you can have machine learning that blocks at the client. You can have machine learning that blocks at the cloud. You can do all of those things. And in the cloud, you can do pretty complex things like do a sample request and a quick extraction of features that maybe you couldn't do with the client, provide a response back in seconds. You can also detonate files and see what they would do in a sandbox and use those behaviors to detect things as well. Of course, that's a little slower, probably takes a couple of minutes. And then you could have huge computationally intense offline models that maybe take hours to run and can provide responses back in minutes, back in hours. Today, we're going to be focusing on the first two layers, things that can provide protection within milliseconds, again, to protect that patient zero. So there's some pros and cons to using client versus cloud-based machine learning. On the client, it's really fantastic for offline systems. If you don't have cloud connectivity, well, you still need protection for those machines. So if all of your machine learning is packed into the client, those machines can stay protected even when they're not connected. The disadvantage is that attackers can use that to game the system, and they can test and test and test offline, essentially get all of the answers to what you detect, and without your knowledge, because you couldn't see them testing because they were doing it in an offline environment, use that to attack people in the wild. It's a little harder to do with cloud. With cloud-based machine learning, if you're providing your blocks from cloud, well, they've got to talk to your cloud. So you have the opportunity to see adversarial attempts that are trying to test your systems to see what it can detect. I want to talk about a couple of adversarial examples, some that are theoretical. And for the most part, most of these examples require some insider knowledge, so keep that in mind. When you're training a model, there are multiple levels where an attacker could trick your machine learning into having the wrong decision. And they could cause you to have a wrong decision by fooling the system to think that something that's malware is actually clean, or the inverse, cause a false positive. We'll start with the sample phase. So before you train a model, you have to create your sample set. And there are a few ways where an attacker could tamper with that sample set if they have access to it and if they're able to change those labels. So they could send an influx of new samples to completely confuse your model. They could change the ratio that your models use to train, which can be very disruptive for a model. They could flip the labels. They could say, hey, these things that you had labeled clean, I'm going to flip the label to say that it's malware. And all of these things could cause your machine learning model to respond with the wrong answer. If they know what your features are, they can do things like feature evasion. So they know what features are important to you, they just remove those features from their malware. Now, if you're using behavioral ML, it's a little hard to do. If you can't do the bad behaviors, it's a little hard to hide, but when you're talking about some of the other models that are focused on properties of a file or other types of attributes, you can do some feature evasion. You could also inject clean features into malicious files and confuse the model. Maybe the prediction won't be strong enough because of those clean features and will cause the model to fail. If the attacker knows what model you're using, what parameters you're using, and can get a rough estimate of your sample set and your features, well, they can just build your system offline. And they can test it all they want, and they can figure out exactly what your model will say when they throw their malware out there. And last but not least, if they don't have access to any of these things, but they have some indication of what you depend on for features. There are some new black box interpretability methodologies that can give them a rough idea of what features are most important to your models based on their testing that they're doing. Of course, if they'd have to connect to your cloud or your client to get those answers. And then there's cats. All right, I've seen a million pictures of kittens, but as cute as they are, we thought we should go big or go home, okay? So this is a cat. He is as big as my child. I think he's much cuter than a kitten. His name is Zuko. He's watching you. Okay, back to business. All right. right, so I want to talk about some attacks that have actually happened. This first attack was on our automation systems, but it could have just as easily caused problems with our machine learning systems. This was an attack where someone took clean files and tricked antivirus vendors into detecting them. This was presented at Virus Bulletin a couple of years ago. Full details in the paper there if you want to go look at it. Essentially what they did is they took antivirus clients offline, did some testing to figure out what those antivirus clients were using for detection. So imagine a file has got some command and control server embedded within it. They would use testing those strings to see what components actually cause the antivirus engine to detect. And then using that knowledge, they also studied how those antivirus engines were detecting files. So what parts of the file did they use to detect? And in some cases, the part that they used to detect didn't always match up with where the malicious content was. So they paired those two pieces of knowledge together, and they took a clean file, injected malicious content into the part of the file that was not used to detect the file, and then submitted those tampered clean files to VirusTotal, which is an exchange partner for many antivirus vendors. What happened is that as antivirus vendors started collecting those samples from VirusTotal, their automation systems kicked off, saw those malicious strings, and then created detections for those files. And unfortunately, the detections were on the clean part of the file, which ended up causing the antivirus engines to detect the real clean files in the wild. The second example is focused on cloud-based evasion. So in this case, the attacker was trying to tamper with our certificate-based reputation system. And they were spoofing lots of traffic into the system to attempt to gain reputation quickly on these digital certificates that they were then going to use to sign malware. And they were so profuse. So this was really a high volume attack. We spotted it through some of our basic telemetry metrics that tell us how good of a job we're doing classifying traffic. We saw that our classification ability dropped way down, and we were able to kind of spot this attack. Once we looked into it, we saw, hey, there's also other attacks happening on unsigned files and also very low-level attacks. Found out that this had been a problem for a little while. So what did they exploit to be able to do this? Well, they guessed our feature set. I mean, for reputation systems, it was pretty simple. It was time and traffic and the digital certificate. These are pretty common features of a reputation training system. So what we did is we built a complementary model to be able to filter out that attack traffic. And this was really an early precursor to an Ensemble approach that we're going to talk about in depth today. There's been a lot of research that talks about the types of attacks on singular models and how it's pretty simple if you can guess the sample set, the features, any of these components, you can trick the model into making the wrong decision. And a lot of that research has pointed to this approach of using ensemble models to help filter out that noise and ensure that it's not as easy to tamper with the singular models. And I'm going to turn it over to Jugal to talk about the research and development we have done to apply this ensemble approach.
Thanks, Holly. So before we dive into that, a quick show of hands. How many of our folks here know what stacked ensembling or stacking is? All right. Seems like maybe 5 to 10%. And how many of you folks have actually used this technique in real world to catch threats? Randy, you're not allowed. All right. Seems like it's no one. Great. So everyone here is about to learn something new, and I'm excited. So let's take a real world scenario. Let's assume that you have a medical issue. A great way to start the talk, right? You go to this doctor, you get some diagnosis from him, and you're not so confident about his diagnosis. You go visit a specialist. You then go visit this guy and this guy. If the diagnosis is very similar, you now have a good amount of confidence into what your issue is. The point I'm trying to make is you're basically combining the strengths of all these specialists to determine what your medical issue would be, and then taking next steps. Well, stacking works in a very similar way. It is basically an ensemble technique that is used to combine the strengths of several base classifiers. The base classifiers are trained on your complete data set. We look at the predictions from these classifiers as input features that go into the stack classifier, and then you look at the output from the stack classifier and use that as your final verdict. Now, this is a very popular concept and a very well-known thing in the Kaggle community to win several machine learning competitions. But what happens when we take this concept and apply it in real world to catch threats? How does it deal with an active adversarial environment where adversaries are constantly trying to hide themselves, against our defense mechanisms? How does it do when the data set is completely has covariate shift? The threat landscape changes very rapidly. How does it do in terms of noisy labels for training? How does this technique scale when it's used to correlate petabytes of information daily? And most importantly, how does it perform when it's used to evaluate over 2.3 billion queries globally each day? By the time I'm done, I hope everyone in this room knows exactly what stacking is in details and is able to leverage some of our experience and lessons that we learned when we tweaked and modified this technique to make it work in a security context. So let's dive right into it. Diversity. Building a diverse set of base classifiers is the most important thing in not just generating an effective stacked ensemble, but also to make sure that your ensemble is resilient to adversarial attacks. This diversity can be achieved through different feature sets. You can have features that represent the static, dynamic, contextual, or machine attributes. You can also have different featureization techniques used on the same data. You could do different training algorithms, from linear classifiers to ensembles to deep neural networks. You could have different training data sets where you optimize on PE files versus non-PE files, or you look at specific data sets for file types. And then you can optimize on different optimization settings, depending on what you want the classifier to handle. What sort of threat scenario do you want the classifier to handle? In terms of feature sets, since all of us work in security, we are lucky that we already have a very high dimensional data. We can look at machine attributes from a potentially infected machine, like the OS version, security settings, locale, and so on. We can look at static file attributes, like the partial and fuzzy hashes. We can look at the full file content, the header, footer. We could look at file properties like the file geometry, file size, file metadata, signer information. Add that up with behavioral and contextual data, like what sort of APIs the file calls, does it do any process injection, what's the child-parent relationship between a file. And most importantly, we can also leverage our researcher expertise that can help us define custom features to better classify a file. At Microsoft, we use a very similar data set to generate hundreds and thousands of different unique feature representations. And more importantly, we make sure that these features are updated every day so that the features are relevant to the current threat landscape. Diversity in different set of classifiers comes naturally if you have a high dimensional data. Different classifiers perform differently when your data distribution is different. It can also perform differently depending on the number of features that you have. If you look at the table here, we see that a boosted classifier performs well with behavioral and fuzzy data when the total number of features are anywhere from 500 features to over 6 million features. Whereas a linear classifier like average perceptron does better when we combine static, dynamic, and contextual data, and the number of features goes all the way up to 16 million. And then a deep neural network can handle more of the raw data that you get from file detonation and file emulation. Moreover, you can take a combination of these classifiers and further optimize them to either deploy on the client side, on the cloud side. You can also have models that look at the full file content itself. Once we have this, we can optimize it for different file types like executables, JavaScript, VBS, PDF, macro, and sky's the limit, right? Just looking at these different combinations, you can generate over hundreds of different classifiers that would be diverse. So before I get into how do we optimize for different threat scenarios, let me re-emphasize on how highly polymorphic our current threat landscape is. 96% of all malware encounters are only seen once on a user machine, and they are never seen again. Out of that, the remaining 4%, you see most of the traffic is in the first 2 or 3 hours. After that, it pretty much dies off. As Parikh mentioned in her keynote, we are in a real-life version of whack-a-mole. We have got to get it right the first time. If we miss it, we are not going to be able to protect that customer. Now, one way to cope up with this is training and releasing your classifiers at a fixed cadence, time cadence. You could have classifiers that get trained and released multiple times a day. These classifiers would be very sensitive to changes in your data distribution as your threat landscape evolves in the same day. They can help you catch more new variants of polymorphic threats. Similarly, you could have classifiers that are trained and updated every 24 hours, every week, and every month, depending on the model TK rate. Not only that, but instead of just having a malware classifier, you could have classifiers that are optimized for clean files. They can basically give out a high confidence for clean files, for PUAs, which help us classify potentially unwanted files. You could have classifiers that are optimized to work on specific enterprise environments. We've all seen that the data distribution in enterprise versus consumers is quite different. So the value we get out of this is definitely good. And then, as I mentioned, we can also have classifiers for different file types. So we talk about all this diversity, but is there a way to verify how diverse these classifiers actually are? Are they just adding redundant information, or do they actually provide some value? A quick way to do this is by looking at correlation between different classifiers. Over here, we look at Pearson correlation as a metric. I know the numbers are a little hard to see, but the darker the block, the less correlated each and every feature is. Ideally, we'd want every block to be darker, except for the diagonal elements, which are the same feature with the same feature correlation. Whereas if you see most of your blocks here are light, you pretty much have to go back and make sure that your classifiers that are being generated are diverse. In our case, we could see that most of these blocks are dark, which means that the features were not so much correlated. In other words, every classifier in the collection had something unique to offer, which further strengthens our case for building a stack classifier. Now, we've covered quite a good amount of ground here, and we are only just getting started. Let's take a quick AI break before we dive into the next topic. What do you say, Holly? What's your best fun over here?
Okay, this is my favorite one. So why don't neural nets mind the code? Because they can just add more layers. Oh, come on, a few giggles. I heard a few. Some of you get it. Okay, good.
All right, so we talked about generating a diverse collection of base classifiers. Moving on to the next step, how do we optimally combine the strengths of these different classifiers? Well, there are two widely used approaches, Boolean stacking and logistic stacking. With Boolean stacking, you basically look at the binary outputs from the base classifiers, which is 0, 1, and you treat them as feature inputs for the final stack classifier. With logistic stacking, you swap the binary outputs to model probabilities, which is basically a continuous 0 to 1 value, and you use that as a feature set. When we evaluated our experiments, we found that in a security context, Boolean stacking wasn't really doing so well. The stack classifier wasn't able to outperform some of our single best base classifiers. Moreover, we also found some signs of overfitting, where the stack classifier was basically just trying to memorize the training data and wasn't generalizing as well when shipped in real world. However, logistic stacking seemed to show promising results. the stack classifier was able to outperform all our base classifiers, and we decided to go ahead with that. So we talked about combining these models. Now, how about the model itself? What model should we pick as the stack classifier? Should we go with a linear classifier, an ensemble, a GNN? Before I dive into details there, let me give you a brief idea on our experiment setup that we use to evaluate all our experiments. We basically take a subsample of our telemetry from the past n months, and we split it into train, validate, and test sets. We ensure that none of the samples from train and validate are part of the test set to not have data leaks. We also make sure that the labels that we use for training are not really the most current labels, but are actually labels from the last day of the training window. This helps us ensure that there are no label leaks. We use the train data to generate a supervised model, which is then optimized on the validation dataset, and later evaluated on the holdout test set. Following this strategy, we tried 6 different classifiers to see which classifier was a good potential candidate to be used as a stack approach. We see that light GBM gives us best results at a low false positive region. So we decided to go with that. A quick recap. We talked about generating diverse set of base classifiers. We talked about using model probabilities as your input features to train the stack classifier. And we talked about using light GBM as the stack classifier itself. Now, we plot the ROC curve for the stack classifier versus some of the top base classifiers to see if our hypothesis is actually true. If you look at the results are awesome. As you can see, the stack classifier on the top, which is the dotted line, significantly outperforms some of our top base classifiers, even at a low false positive region. You can also see that this approach is helping us average noise from all of our base classifiers to give out this really nice and smooth ROC plot. When we look at the raw numbers, we can see that we get roughly 92% recall at 97% precision on the test set. So it's all good, right? We have the right model, everything is good, why not ship it? We took that model to evaluate on 60 minutes of live data, and our recall dropped to 9%, and the precision dropped to 13%. Yep, life is not always as easy. Do you guys know any guesses on what might be causing this? What's that? So the validation was good. We made sure that there were no data leaks there, but it was something similar. Let me quickly go over that. So the major culprit we found was indeed data leaks. So in security, we basically trained the classifier on past data, and we evaluated on future data to make sure that it is able to catch emerging threats. Data leak is when information from the future somehow finds its way into the trained data and leaks. If you look at the metrics, we had almost a 10% drop in our recall after we filtered out the data leaks. And we found that even though we made sure that the validation and test data sets weren't leaking, there were some features in our arsenal of 20 million plus features that were directly correlated to the label, causing an optimistic assessment of the model performance. Filtering these out was very important. Let's look at a second scenario, handling missing values. If you look at the right side, you'd see a real-world scenario where this is a clean file, and most of the classifiers don't have a verdict, but 2 of them have a very low probability of the file being classified as clean. Now, my intuition says that the stack classifier would probably use this and maybe come up with a very low probability number of the file being clean. But no. The stack classifier actually thought that the file was malware with a very high probability, a probability of 0.92. Again, life can be hard at times. So, with usual machine learning, people tend to remove instances where the number of features, more than X% of features are missing. But since this is a very optimized scenario where different classifiers are optimized on different threat settings, we still wanted to retain it. But we added a Boolean feature indicating which of the classifiers were missing. And then we do a cross-join between these features. So this helps the model to understand different relationships and patterns between different classifiers. Another approach is using an interpretable model as a stack classifier. This helps us better debug on what might be causing these issues and how can they be fixed. We also find that using unsupervised techniques help us boost our recall rate. We cluster our data, and then we use the distance between each instance to the center of the cluster as features. A quick question. Do you guys know what this plot is? It's a function of time. I showed it before. Let's see if you guys were attentive. What's that? It was the telemetry. So this was basically the volume of telemetry that we receive every day. You can see it's highly volatile. All of the classifiers are optimized assuming a specific data and label distribution. If the data telemetry is so volatile, your classifier is not going to be performing at its best if you're training it on a very irregular cadence. So we make sure that our data and label distributions are reasonably fixed. We also continuously monitor some of our incoming telemetry to catch anomalies or outliers like an outbreak detection or a release of a new software. And we remove that from training our model. So that's great. The model is deployed. But is it resilient to adversarial attacks? Before I get into that, one more AI break. What do you think, Holly?
Okay.
Yeah.
So, wait, I forgot my favorite. Oh, yeah. What do you call a model that spends too much time at the gym? Overfit! Yes! Awesome. Did you read the slide?
All right. So let's take multiple scenarios where an attacker can compromise some of our machine learning pipelines. We start with the scenario where the attacker is compromising some of our models. So to give you a better understanding, we train our models, we train the stack classifier, and then we ship it to prod. But somehow the attacker is able to compromise one of the top classifiers, which is being used as an input feature by the stack classifier. And instead of giving the right probabilities, it's now just giving rogue, noisy values. The question here is, how well does the stack classifier perform when in real-time inference, it has noisy inputs, and it's not trained on that, so it's not aware of this? Well, it actually does quite well. When we look at some of our experiments, with 0 instances perturbed, we see that the classifier at 1% false positive rate is at 85% recall. And even after you perturb all the instances of that top classifier, which is being used as an input feature, the performance of the stack classifier drops down to roughly 70%. It's way better than how individual base classifiers would do. Let's consider a second scenario where the attacker somehow gains control of our features that we use to train the classifier. Extending the case 1, we basically now are training the stack classifier on noisy features. So we are adding anywhere from 1 to 10 different input features that are being used by the stack classifier. And all of them are noisy. So the question remains, how robust is the stack classifier to noisy inputs? When we look at it, the classifier is able to actually detect all 10 of these features as noisy. And when you look at the plot on the right, the feature importance is actually quite low for them. So the classifier knows that these are noisy, and it doesn't really train on them. So when you ship it to prod, it's actually doing quite well. Even when you look at the numbers, even after adding 10 noisy classifiers, my false positive rate increases by roughly 0.4%, and my true positive rate decreases by roughly 0.3% only. Let's consider a case where the adversary is able to craft special adversarial ML attacks that is, targeted misclassification. So now, let me describe the scenario. We take a PE file, we featureize it, we run it against our models, and the model says it's malware. Now, we attack the features with JSMA. So to give you a quick overview, JSMA is a very commonly known white box adversarial ML technique, which basically looks at your features and perturbs them in a way that the same model now thinks that the file is clean. So this is targeted misclassification. What we did here is we took the top 2 classifiers that the stack classifier was using, and we photo a bit. So basically, we flip the labels. If it was malware, we flipped it to clean. If it was clean, we flipped it to malware. And we compared the results of the stack classifier at 0 perturbation, it was at 85%. And even if we assume that the attacker is able to compromise all the instances from those top 2 classifiers, the performance dropped down to roughly 65%. Still not that bad, right? So how about a scenario where the attacker is just motivated enough to just break our stack ensemble in ways that we don't see it coming? Well, we have real-time monitoring in place to measure this. From a samples perspective, we look at the total number of instances that come in for training the model. We look at the data distribution, make sure that we don't have a significant shift in data distribution. We look at biases, where the model should not be significantly biased to a specific threat family or a specific clean file. And then we also look at anomalies in there. From a features perspective, we make sure that our features are still relevant. There is not a significant covariate shift between what we used previously and what we are using now. And it is still used to, describe the current threat landscape well. In terms of models, we ensure that all the models that we ship are meeting some of our metric requirements. And once the model is shipped, we do continuous monitoring to ensure that the model doesn't go rogue. We look at the overall blocks at a minute-by-minute cadence, and we also look at the telemetry to make sure that there are no anomalies there. I strongly believe that transparency and collaboration is the way to go in the security industry. After all, we're all trying to make the world a better place, right? I really hope that these results are encouraging enough for you guys to try this on your environment.
Great. So let's talk about some of the real-time results that we had from these models. The initial testing was very promising. And in fact, when we deployed it, it actually outperformed our projections. So these models today are providing about 12% of our cloud blocks in June. And to give you an idea of scale, we're talking about 9 million attacks that these blocked in 1 month alone. So this is pretty huge. And it's not just doing well against PE files, it's also doing well against other types of files. It's blocking malicious JavaScript, malicious VBS files, all types of files. One bonus that we didn't anticipate was interpretability. So if you think about some of the models we talked about earlier, some of them have millions of features. And when you're trying to troubleshoot, why did a model make a bad decision? It's hard. The really nice thing about the Ensemble approach is that you've got a pretty limited set of features. You're using the probability scores of the other underlying models. So it's pretty simple to see why the model made a blocking decision versus a bad clean decision. On top of this, when we take slices of our data, we can look at the Ensemble blocks that are successful against, say, a particular type of threat like JavaScript. And then we can compare that to how our JavaScript trained model is performing. And it helps us find gaps within those individual models. So we can use it to make our base model stronger, which will then make our overall prediction stronger as well. So let's quickly go over the benefits of using the Ensemble approach. It's great at filtering out noise from misperforming models. It's great at covering the gaps of models that may be underperforming. It clearly increases your predictive power. We've got a 12% boost in the month of June alone. And it adds a layer of resilience against attacks for single model adversarial attacks. I want to talk about a couple of real-world case studies where the Ensemble models helped us out. These case studies focus on the client and cloud machine learning models working together. This first case study is interesting not because it was huge. It's actually very interesting because it was tiny. This affected around 100 people in central and western Canada, and it was a spear phishing attack against primarily businesses. About 73% of the targets were local businesses. And this happened in a flash, so most of the targets had opened that email in the first 5.5 hours, so you really had very little time to react. Started out with an email that came from what looked like their landscaping company with a PDF invoice attached. Once they opened that invoice, it looked like a DocuSign agreement, and once they clicked that link to the DocuSign agreement, it took them to a phishing page, which then tried to steal their corporate login credentials. How did that work? Our local machine learning models extracted features from that PDF file, saw enough suspicious results to say, I need to ask cloud about this file, sent that metadata up to the cloud where our machine learning models ran on that. Unfortunately, if you can see there, our PDF model did not have a good response. Luckily, the Ensemble was there and looked at a collection of other model results and realized, yeah, this thing is malware, this is bad, sent a response back to the client within milliseconds, and before that file could execute, it was blocked. The second example is larger scale attack. It is focused on Brazil, and it was a JavaScript banking Trojan. So this attack happened through a series of events. So the target was sent an email. That email had a zip file. Inside that zip file, there was a VBS script that looked like a document. And when you open that, it installs a malicious Chrome extension that then actually drops the payload, which is this JavaScript file. And if you see some unobfuscated bits there, you can see that it's trying to steal some banking information from the target. This example was pretty similar. Our local-based machine learning model extracted some properties, saw that this JavaScript looked pretty bad, sent that response to the cloud. That cloud ran our various machine learning models, including the ensembles. Our JavaScript classifier had an okay result, but it wasn't strong enough to block. Luckily, the Ensemble model saw that this collection of responses meant that this was malware, sent a response back to the client, blocked that file before it could execute. Few last words here. A huge thanks to the people who contributed to this project. There's a long list of folks that some are here, most are not here. We've got Randy in the audience. A big shout out to everyone who helped. There's a couple of references here. There's a blog post going live today that has details about that Brazil attack that we just talked about, and an upcoming conference presentation at VB. If you happen to be there, we'll have some related content. Some key takeaways that I want to stress before we hop out of here. A client-based machine learning approach is great if you have offline clients, but once you are cloud connected, you really do need to back that up with cloud-based machine learning. It's the best way to build resilience against adversarial attacks because they can't do that brute force testing offline. Before you start to think about an ensemble approach, you need to make sure you have a really good base set of diverse models, like Jugal talked about. Use different sample sets, train specific models, use different types of models. Build that diverse set before you try to layer that ensemble on top of it. Once you've built your system, consider the most likely methods that an attacker could use to attack your system, and then try it. See if you can break your own stuff. And if you see gaps and you see holes, go back to the drawing board. Look to see if you have you need to have more diversity. Run that Pearson chart so you can find out where your gaps may be. And last but not least, once you've deployed, ensure you've got great monitors to ensure that you can detect those adversarial attacks when they happen. Thank you very much for listening to our talk. We may have a few minutes left for questions. And also, we are hiring. If there are any data scientists in the crowd, any folks who do reversing, security engineering, threat hunting, we have lots of positions open. Please talk to us. 5 minutes for questions? Thanks.
Hey.
Hi.
I'm over.
Where are you?
Where are you?
Like this.
Slightly right, center room. Okay, it doesn't matter. Just hear my voice. So thanks, it was a very broad talk. With regards to deep learning, sure, like ensemble learning, adversarial training definitely helps, but really at the end of the day, it's really you're putting in data, you've got some parameter, you've got a label, and you've got a loss mechanism. So long as you as an attacker have access to that loss mechanism, and you can tune your data, I mean, isn't your system still susceptible? Is there any kind of takeaway here that's,
everything.
New insights in adversarial attack prevention, basically.
So that's a very valid point. And when we look at academic papers, they say that Ensemble would not perform well with adversarial ML attacks, but they don't talk about using a diverse set of classifiers. I think most of them look at ensembles, but it's the same. It's a different variant of the same architecture. So what we are talking about is looking at it from a broader perspective. The other thing is that loss function, we don't train these like. The attacker would have to have access to each and every of our base classifiers to control the input and then look at this tag classifier. So it just makes it that much harder for an attacker to trick our systems.
Okay, cool. Thanks.
Sure.
Hey there.
Hey.
So I had a quick question. So yeah, you're crafting adversarial samples for these ingredient models that are added to the Ensemble. And so I get that like maybe if you see something suspicious, you send up to the cloud to like run all of your models and do the Ensemble. But did you try crafting adversarial samples on that Ensemble model directly? Or are you not really doing that since you can sort of rate limit the amount of times people can test out results on like the Ensemble model as a whole? If that makes sense.
Right. So for the Ensemble itself, we did not, because when we consider a real world scenario, it's going to be very tricky for the attacker to even get to that Ensemble attributes, right? So it's basically adding one more layer of defense on top of it. But yes, if you want to perform a white box attack on the Ensemble directly, it could break it. But then again, the features are not really generated on the client side or on the cloud side. They are generated in real time as this thing is scanned. So, if you consider a real world scenario, it makes it very difficult for an attacker to do that.
Okay, cool. Thanks.
Sure.
Thank you very much for a very good talk, and I really like the idea. You've probably seen the paper titled Ensemble of Weak Models Doesn't Really Make Resilient Models Adversarial Examples. I just wanted to point this out. You said that your model is more diverse, and that's why it works better, but then you say with JSMA, you haven't specified the constraints on the JSMA, how much perturbation you're allowing it to perform. But with JSMA, it performs with 65% accuracy. Let's say that there's a sample within the remaining 35%. Is that sample going to be uploaded to the server as a sample of a goodware or benignware? And then would that cause a poisoning attack in your data set?
Right. So yeah, I very much know the paper that you're talking about. I think that was from Don Song from Berkeley. And to reiterate the point, I think that was on different variants from the same architecture of neural nets. When you say, when the attacker GSMA is still a POC concept, I agree. But if an attacker runs some aggressive models like angry or something like that, a black box attack, it would still not cause poisoning to our data because we have multiple different, sensors and monitoring, even at a telemetry level, to make sure that we identify such things before training our stack classifier.
Do you provide the details of those monitors in your paper?
I think some of it we do, right, in terms of the monitoring, or
not a lot of detail.
Okay, but we're happy to talk to you about it.
We can talk to you. Yeah.
Okay. Thank you.
Thanks.
So I was curious, so you're splitting up your data into a training and holdout set based just on time. And I was curious if you've looked at, for example, most examples of malicious PEs are very slight variants of other malicious PEs. And so even if you're splitting it up by time, there's going to be a lot of near duplicates in both your training set and your holdout set.
Right.
Right? So I was curious if you've dealt with that in any way.
Right. So that's a very good point. I think some of the approaches that we look at, instead of looking at the file hash itself, we look at more fuzzy hashes, right? Like things that consider these small variants and don't give out a new hash, even if most of it is similar. If you just change a variable name, that gives you a very different file hash. But when you consider fuzzy hashes, the value would still be corresponding to it. So that helps us in, preventing those leaks and not considering a very slightly different variant of the same file which was present in the trained data. We also look at different, I think we can take it offline. I think we're out of time.